Hey guys, so this lesson is for Tuesday, March 31st, and we're going to continue our discussion on scatter plots, but we are going to be looking at the relationship between two numerical values when they are linear and when they're not linear, what they resemble and what they look like. Before we do that, I want to go back over the two homework questions I had on the problem set yesterday for you to make sure that you were reading the scatter plots correctly. So the first was 3 and 4, and they asked, is there a relationship between age and the finish time in a race? And so the older the person got, the longer it took them to finish the race. Does that make sense? Yes, it does. So if you look at this one actually kind of makes like a curved mark. It's not very linear. And it does show you that, yeah, a 70-year-old takes 300 minutes, where a 20-year-old only took 200 minutes. But that makes sense because an older runner is going to take longer to finish a race. And then looking at S89, this was the other one you had to look at. This is the weight of a horse and its baby's weight. And so it shows that, if I can kind of notice that all of them kind of make sort of an upward linear pattern. So the bigger the mare, the bigger the foal size. So there is a relationship that the larger the mare, the larger the baby is going to be on this one. All right, so going into today's lesson, it talks about how not all relationships between numerical values are linear. And we saw that before, but now we're going to really hone in on that. There are many situations where the pattern would be better described as a curve, and we know two curves. We know quadratic curves, and we know exponential curves. So those type of curves can help us to kind of look at a pattern and see if it resembles more of a quadratic, which would make the U, or if the pattern maybe resembles more of an exponential pattern, like here's an upward sloping, here's a downward sloping, and they would both kind of resemble that exponential type. Go to S92. This is lesson 13, by the way, S92, and they give us some scatter plots. These are the 5 scatter plots we talked about in the last lesson. And if you notice, the questions on S93 ask questions about these scatter plots. So it says, which of the 5 scatter plots from lesson 12 show a pattern that could be reasonably described by a quadratic curve? So what I like to do is I like to look at them and kind of see where the dots are going. So if I look at this one, the dots are pretty much going down. And this one, the dots are pretty much kind of doing that. That's very exponential looking. And this one, they're kind of just like all over the place. This one looks like, oh, look at that one. That one took on a very U shape. And then this one, they kind of sort of going up. So you can kind of draw which, and kind of get an idea of where the dots are going. So which one looks most exponential? I would say scatter plot 4. And which one could be described by exponential? Definitely scatter plot 2. Whereas I saw 1 and 5 looked more linear, and 3 looked like it was just all over the place. So on S93, it says, let's revisit the data on the elevation and mean number of clear days. Remember, we talked about how the higher it is, the clearer the sky. The scatter plot of the data is shown below, and the plot shows a straight line that can be used to model relationship. The straight line is not perfect. It is not on every single dot. It is on 2 dots, though, if you look at your book. So it does use 2 of the dots that kind of resemble it. And if you notice, you draw like a potato around all the dots, and then you kind of draw in the middle. That's how you can get your line of best fit. So it kind of gives you an idea about where that line would be. So there are 2 ways that you can find this. This is what we call our line of best fit or our line of regression. In 8th grade, what you do is you find a line of best fit like this, you draw it, then you pick 2 points and you find the slope and the y-intercept. And you make what they call an estimation line for that line you drew. In 9th grade, they actually teach you the line of regression in a calculator, but since we all don't have calculators, we'll just have to wait till we get back to the classroom to kind of show you that. So this right here, this linear line, 83.6 plus 0.008x, that is an estimated slope and an estimated y-intercept for this line. So I could make guesses off of this scatter plot by using this equation. So it says, assuming that the 14 cities used in this scatter plot are representative of cities across the US, should you see more clear days in Los Angeles, which is by sea level, or in Denver, which is the mile-high city? Well, what did we learn? When the elevation goes up, the clear days go up. So the higher the land, the more clear days. So Denver should have more clear because it is a higher elevation. And I know this to be true because my sister lives there and she has a lot of very pretty days of weather. She has a lot of cold days, but a lot of pretty days. So if we turn the page, it says one of the cities in the data was Albany, New York, which has an elevation of 275. If you did not know the mean number of clear days for Albany, what would you predict the number to be based on the line that describes? So if I have an elevation of 275, which is about, this is about 500. So 275 is about here. I would predict it to be about 90 days of sunshine. So 90 days approximately, use that approximate symbol. Albuquerque, New Mexico has an elevation of 5,311, much higher. So if I go back to my chart and I find 5,311, which is about here, that's going to tell me I'm going to have about 110 days. So I'll have approximately 110 days of sunshine. Let's go to the next one. So example 2 is a quadratic model. And you can notice that the dots actually look like they make this kind of curve. I draw right on my scatter plots, okay? And so it's showing us that as it gets to about 200, it yields a lot more. But once it hits 200 grams of fertilizer, it starts to go down. So we see with the quadratic pattern, a decrease in the amount. So then let's look at example 3, which would be an exponential model. And if you can tell, this is the shell length of a lobster and its age. And look what happens to this data. See how it makes more of that exponential curve? So as the shell gets longer, the lobster is much older, which makes sense. And then here's another model on S97. That's the same one. They've drawn the same line that I just drew. And it's asking us to just discuss what do we see. So if the lobster has an exterior shell of 100, which is about here, you could expect it to be about a year and a half old. So you can use the dots to kind of guess on any of these graphs where about the answer would be. Okay, so for problem set, go ahead and do number 1 and answer the question for that. And then you could do number 2 by plugging into this equation to create the table. And then do number 3, which is another model. And then we'll stop there. You do not have to do 4 and 5. So 1, 2, and 3 on S98 and S99.